Welcome back to the final video for Digital Systems 1, and this video we're going to discuss modifying a counter. So in the previous video we discussed asynchronous and synchronous counters. Now we're going to learn how to modify them in case we don't want to use every state available in the output of the counter. So on the screen here you'll see a state transition diagram. The arrows indicate how one state changes to another in response to an input clock pulse. Think about this as the outputs of a counter. In this case, we have a 3-digit number, so we know that this is a counter that has 3 flip-flops. And if a counter has 3 flip-flops, we know from the last video that the mod number would be 2 to the 3rd, or 8. That would be the mod number, which means we know that there are 8 states. If there are 8 states, we can expect that counter to go from 0, 0, 0 to 0, 0, 1 to 0, 1, 0 to 0, 1, 1 to 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. That's how we would normally expect that counter to operate. But what if we didn't want to count up from 0 to 7? What if I only wanted to count from 0 to 5 and then reset? What if I didn't want these states to occur? How could we make that happen is the question that we're going to answer today. And we're going to do that by learning how we modify a counter so that it can operate with a smaller mod number than the number of states available. So we know we have 2 to the n states available. What if I want a mod number that's less than that? What if I want a mod 5 counter or a mod 3 counter instead of a mod 8 counter? So that's the question that we're going to answer in this video. So to change the mod number of a counter, you first have to determine the least number of flip-flops needed. So for example, if I want a mod 11 counter that counts from 0 to 10, I need to know, well, how many flip-flops do I need for that? The least number. Could I use 12 flip-flops, 3 flip-flops, 2 flip-flops? How many do you need? So determine the number of flip-flops you need to count up to that number. Remember, you need 1 flip-flop per digit in your number. So if you have a binary number with 4 digits that you want to count up to, you need at least 4 flip-flops. Next, we're going to implement the idea of a NAND gate to force the flip-flops to be cleared when you want to reset the counter. Remember that we talked about asynchronous override inputs. And we're going to be using those asynchronous override inputs today by connecting a NAND gate to the clear input of your flip-flops. The NAND gate at a certain point is going to force those flip-flops to be cleared instantly, causing the counter to reset back to 0 at the time that you want it to. Here's an example of how we might do that. So let's start by identifying what type of counter is this? Synchronous or asynchronous? It's going to be synchronous because all of the clock signals are connected to the same clock signal here. Remember that an asynchronous counter or a ripple counter has the output of one flip-flop connected to the clock input of the next. So we have a synchronous counter in this example. And what I'm going to show you will work for a synchronous or an asynchronous counter. But in this example, we have a synchronous counter. It's got 3 flip-flops. 1, 2, 3. So that means it has 8 states. And we would expect this to normally count from 0 to 7, from 0, 0, 0 to 1, 1, 1. But now take a look at the NAND gate right here. So the NAND gate is connected to each clear input on the flip-flop. So reminder, the clear input is an asynchronous override input. That means that if you want to force the flip-flop to be low, you have to apply a signal to these clear inputs. And these clear inputs are active low inputs. If I want to force the output of the flip-flop to be cleared, if I want to force the output of the flip-flop to be 0, I have to send a low signal to each one of these inputs. So imagine if I could identify a time where I only want the counter to count up to maybe say 5 or 6, whatever. Maybe if I could identify a time where I want the counter to reset, I need the NAND gate to then send that low signal to all of my clear inputs. Once the NAND gate sends that low signal, the flip-flops will all be cleared instantly. Because these are asynchronous inputs, when you apply a low, the clear happens instantly, which means the counter will reset back to 0, 0, 0 anytime that NAND gate sends a low signal. So now, look at what the inputs of the NAND gate are connected to. Input B and input C. So remember a NAND gate has the exact opposite output of an AND gate. So a NAND gate will always have an output of 1 unless both of the inputs are high. If both of the inputs are high, a NAND gate will output a 0. Go ahead and take a minute to review the NAND gate if you are not remembering the truth table at this point in time. So a NAND gate will output a low when B and C are high. So input B is coming from this flip-flop. You can imagine a wire coming from the output here to this input. Same thing for input C. Input C is really coming from the output of flip-flop C. You can imagine a wire going from flip-flop C down to this input. So when B and C are both high, the NAND gate will send a low signal to the clear input of all 3 flip-flops, and the counter will start over counting from 0. That's how we clear it out. So my question is, if B and C are going to be high when this NAND gate sends the signal, how have we changed the counter? What is it going to count up to now? Let's take a look. So here's our circuit where B and C are connected to the NAND gate. So let's assume it just starts counting from 0. It's going to go 0, 1, 2, 3, 4, 5, and right here is when B and C are both high. So it's going to get through all of these counts. It's going to go through each one of these states, and then B and C are both going to be high at the same time, and the NAND gate will immediately clear out the flip-flops. We call this a temporary state or a transitive state. It's a temporary state because as soon as C and B are high, the NAND gate is going to clear the flip-flops so fast, it'll be reset before you ever even realize that the output was 110. It happens almost instantly. So we don't really consider this 110 as a state because it happens so fast you can't physically see it or capture it. So we call that a temporary state, and anything that's a temporary state, we don't count in the mod number. So this counter starts going at 0, 0, 0, goes up to 1, 0, 1, and then it'll reset. We don't count the 110 as a state. So we would call this a mod 6 counter that counts from 0 to 5. And if you were to look at the waveforms for this counter, here's what you would see. A, B, and C are our flip-flop outputs, and here's the NAND gate. And so it's going to start counting 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. And for the briefest second, you can barely even see it before the clear happens. For the briefest of seconds, the NAND gate goes low. The flip-flops are cleared. They're all set back to 0, 0, 0, and it begins counting up again. So this is what the waveform might look like. We actually call this a glitch It's a little blip. It happens so fast that you can't even almost measure it. You almost can't capture it. And if we were to look at the outputs of this flip-flop, if you were to have flip-flop A, flip-flop B, and flip-flop C connected to LEDs, you wouldn't even see the lights blink on for 110. It would be, the clear would happen so fast, you just can't even capture it, which is why we call that a temporary state. And this is what that waveform would look like. So by adding the NAND gate and connecting the NAND gate to the inputs that are high when you want to reset, you can modify the counter to count to a number less than your maximum value. So with 3 flip-flops, I could count all the way up to 7. In this example, we're only counting up to 5 because we're resetting once we get to 6, and that state doesn't count. This is how we modify a counter so that we can count to a number less than your maximum total number of states. So let's do another example where we're going to draw the waveforms for the output of each flip-flop below. We're going to determine the mod number of the counter and also determine the frequency at the output of flip-flop D. So first, let's determine the mod number. The only way we can do that is by investigating what's connected to the NAND gate. So the NAND gate is down here. We can see that flip-flop B, flip-flop C, and flip-flop D are all connected to the NAND gate. So that tells us that when D, C, and B, when those 3 are high, anything connected to the NAND gate, you will say, oh, if that's high, then that's one of the conditions that will cause the NAND gate to clear the flip-flops. So anything connected to the NAND gate, you'll say, oh, those are high. Anything not connecting to the NAND gate, you'll say that's low. So when D, C, and B are 1, 1, 1, while A is low, because A is not connected to the NAND gate, the NAND gate will asynchronously clear the flip-flops. Asynchronously clear the flip-flops. So that means that that clear is going to happen instantaneously. That also means that the counter doesn't really ever get to 1110. That state doesn't count. It's only going to get right up to the state before that. So the counter effectively counts from 0000 to 1101, which is 0 to 13, before the reset occurs as soon as it hits 14. So we say this is a mod 14 counter that counts from 0 to 13. So again, let's review. Mod number is number of states. If it counts from 0 to 13 and 0 counts as a state, that's 14 total states. But it doesn't count up to 14. The last state is 13, which is 1101 in binary. Once it gets to the next state after 13, the clear happens so fast, we don't count that as part of the mod number. That's not a state that counts. So it's a mod 14 counter that goes from 0 to 13 and then resets. Notice this is also an example for a synchronous counter. However, connecting the NAND gate in this way to the clear input of your flip-flops for an asynchronous counter, for a ripple counter, will work exactly the same way. So this idea works for a ripple counter as well as for a synchronous counter. So we've discovered what the mod number is of the counter, and now we're going to draw the waveforms for this counter. So we know what the counter has to count up to. It has to count up to 13 and then reset. Your waveform has to reflect that. And I find the easiest way to start drawing a waveform like this is start by filling in the bottom. Fill in what you know the count should be and identify where the reset should occur before you draw your flip-flop outputs. So I know the reset is going to occur right here after I count up to 13. So sometimes it's easier to draw your waveform by doing the bottom first. Then you can look at what each flip-flop is doing based off of the digit. So for example, I know that flip-flop A is the last digit in each count. And I can see it goes from 0 to 1 to 0 to 1 all the way across. It continues to toggle like it did before. So now you're going to draw in that toggling. So flip-flop A goes from 0, 1, 0, 1, 0, 1, 0, 1, all the way down. Now let's look at flip-flop B. Flip-flop B is going to be 0, 0, 0, 1, 1, 0, 0, 1, 1. You're really going to be looking at flip-flop B and just making sure that you fill it in the way your count is showing you. Notice that we expect, in a normal count, we expect flip-flop B to be low for 2, high for 2. Low for 2, high for 2. Which, it follows that pattern until you get closer to the end of the count before the recycle hits. Notice that it's low for 2, high for 2. Low for 2, high for 2. Low for 2, high for 2. Low for 2. And there's the glitch, where just for a split second, it goes high before the clear takes effect and forces the output to be low, and then it starts over. So there's the reset point where I can see it didn't make it to 15, it only made it to 13 before it reset. We can see with the flip-flop C what the output was going to be. This one we expected to be low for 4, high for 4, low for 4, high for 4, but there's a reset point involved, so it's only going to be high for these 2 points before the reset occurs and everything goes back 0. So if you identify what it's supposed to count up to first, then draw the reset point. You can fill in the waveforms following the pattern that you see, where flip-flop A is low for 1, high for 1, low for 1, high for 1. Flip-flop B is low for 2, high for 2. Flip-flop C is low for 4, high for 4, etc. You can follow the pattern until you hit the reset point. Once you hit the reset point, you just have to start over. That's why it's easier to start with filling in the counts, identifying the reset, then draw the waveforms. So with flip-flop D, we know that one's going to be low for 8, high for 8, but with the reset point here, it's actually only going to be high for 6 spaces before it goes back low. And that's how we can draw a waveform for a modified counter. One of the most important things about your waveform should be that the reset point is very clear, very clearly labeled, just like a solid line here. Label it as the start over, the reset point, and show your counts at the bottom to prove that it goes up to that reset point before starting over. So, back to the original question. We drew the waveforms for the output of each flip-flop. We have determined the mod number of the counter, and we're now going to determine the frequency at our output. Remember, the frequency at the output is equal to the frequency of the input divided by mod number. Here's the frequency of your input, and what was the mod number of this circuit? It was 14. We determined the mod number two or three slides ago when we looked at what was connected to the NAND gate and determined what it was going to count up to. It's going to count up to 13 before it resets. That's a mod 14 counter. So you take your input frequency, divide by your mod number. There's your output frequency. So once we modify the counter, the mod number is no longer 2 to the n. Now, the only way you're going to know what the mod number is by looking at the NAND gate and determining how far it will count up to before it must reset. That's the only way you'll know. You can't just look at the number of flip-flops and say, oh, the mod number is 2 to the n. Not when it's been modified. You've changed the mod number, and the only way to know what you've changed it to or what it has been changed to is to understand how the NAND gate is connected and how the NAND gate will affect the reset of your circuit. So another type of counter is a mod 10 counter. It's also referred to as a decade counter because it has 10 states. A decade counter that counts from 0000 to 1001 is also called a BCD counter because it produces the 10 BCD code groups. Remember, BCD, binary coded decimal, is a series of code groups. Each group is 4 bits. Each group of 4 bits represents the digits 0 through 9. So if a counter goes from 0000 to 1001, it's counting from 0 through 9 using 4 bits per group. That produces your valid BCD code groups. BCD counters are commonly used when a sequence of BCD numbers are needed. So next we're going to construct a mod 10 or a BCD synchronous counter that will count from 0 through 1001. Oops. So I want you to try to solve this by yourself. Try to draw the mod 10, make sure it's a synchronous counter, and figure out what has to be connected to the NAND gate in order to make it count from 0 through 9. So with this counter, in order to count from 0000 through 1001, the reset point must occur when the counter reaches the next state after that, because we want it to get all the way through 1001. The next state would be when DCBA equals 1010. Notice that's when D and B are 1, while C and A are 0. So when you're considering designing a counter and you're trying to figure out what's supposed to go to the NAND gate, write out in binary the number or the state where the reset is supposed to occur. The reset here would occur when the output is 10, 1010. Then look at which bits are high in that number. In this case, D and B are high. So those two flip-flop outputs have to go to my NAND gate as inputs. So to trigger the reset point at the correct point, flip-flops B and D must be connected to the NAND gate. And don't forget that we're drawing a synchronous counter in this example, not a ripple counter. So your flip-flops should be arranged in order to show that. And here's the solution. B and D are connected to the NAND gate. The NAND gate is connected to all 4 clear inputs. You need 4 flip-flops because you're trying to display a number that has 4 digits. And we have the synchronous design where the AND gates are used for the J and K inputs that follow each flip-flop. This would be how we would design a decade counter or a BCD counter that is a synchronous design. For the last question, we're now going to construct a mod 8 asynchronous counter. Remember, an asynchronous counter is like a ripple counter. A mod 8 asynchronous counter. And we're also going to determine if the output frequency of the most significant bit, that's your last flip-flop, is 1 kilohertz, what is the input frequency of the clock signal? First, we're going to determine how many flip-flops do you need. If it's mod 8, that means it'll have 8 states. That means it begins at 000 and it ends at 111. In order to have a counter that counts from 000 to 111, you need 3 flip-flops, and you don't need an AND gate. Because in this case, I don't have any states that I want to eliminate. I want to go from 0 all the way through 7 so that I have 8 states. Here's what your circuit will look like. This is the asynchronous counter, so it's the ripple counter, where the output of one becomes the input of the next. All the J and K inputs should be tied to power. And the input frequency is going to be equal to the output frequency multiplied by the mod number. Think back to the original equation that we discussed, where output frequency was equal to input divided by mod number. So you're just rearranging that equation that we've already provided so that you can solve that for input frequency. Once you rearrange that equation, you'll see that the input frequency has to be 8 kilohertz if the output frequency is going to be 1 kilohertz. Remember that this is also a frequency divider, So if you have 3 flip-flops, that means you have a mod 8 counter, which means your output frequency is going to be 1/8 of your input frequency. So the output frequency had to be 8K because the input frequency was 1K. And that is the end of the lecture on modifying the counters.